What's the derivative of secant x? Secant x, tangent x. Right there.
Oh, okay.
What's the derivative of tangent x?
Secant squared x.
Right there.
Oh.
See, there's your u, and the numerator just now is your what? Du.
Okay.
Yes, sir.
So I get like what the derivative is, but why are we taking the derivative out there?
Okay, because there's a rule that says if you have the u here and you have the du in the numerator, you know that equals what?
It's just ln of.
Yeah. And so what you're hoping is that if this is your u, then this numerator, in order to use the rule, is going to have to be your what? Du. Is that okay?
Yeah.
Now, there is no rule where the du is in the denominator. All right? So don't ever try to make your denominator your du. The denominator is going to need to be your u. And if that's u and that's du, and this has a power of 1, if it had a power of anything other than 1, this wouldn't be the same thing. But it has a power of 1, then you get a natural law. And that's that rule I used yesterday when I was working a problem. I just told you it's a rule that you're supposed to know eventually. And here's how it's written in rule form. The integral of secant u du is equal to the natural log of the secant of u plus the tangent of u. And what goes out on the very end plus what? C. Now, the good news is I would much prefer to just use the rule, but I want to go ahead and show you how the rule came about. All right? That's one of those cool ones. But here's how easy it is if you know the rules.
Mr. Evans, what is L'Hopital's rule? Didn't we like?
Not right now. Not right now. We're not, L'Hopital's rule you will use with this eventually, but not now. Okay, secant pi x dx. Does everybody realize the u is just the what? The u is not the whole thing. The u is only the part that's what? After the secant, right? Does everybody see that? Everybody okay with that? So, there's your u. So what do I need right here to make du? What needs to be written right there? What? Pi. But if I put a pi there, what do I have to put out front? 1 over pi.
Oh.
Okay. U is equal to pi x. I'm trying to use this rule right here. Secant u. So the u is equal to pi x. And I'm going to do what I wasn't going to do. That's your u. You take the derivative of that. Now, since you're in high school, Mr. Evans should write what the du is. Your college professor will never write a du if it's that easy. You're just supposed to know the derivative of that is what? Pi. He knows the rule says it's secant u du, so he needs a what here? A pi. And since pi is a constant, and I put the constant here, what can I do out here? I can put what? 1 over the constant. Then I just use the rule. So it's 1 over pi, natural log, secant pi x, plus tangent pi x, plus c. So if you got the rules, it's easy. See? All the trig functions are really pretty easy as long as they fit one of the 10 rules. Now, if the trig function is not one of the 10 rules, we got ways to deal with that, but not there yet. Yes, sir.
So say you put like a constant on the other side of the integral. Do you have to distribute that to the constant?
I'm not sure what. If you put a pi here, you got to put 1 over pi here, and it's 1 over pi times everything in that interval.
Yeah, I'm saying when you add the c at the end, does the pi?
Okay, what's a oh, technically you're right. It is 1 over pi times that. But what's a constant times a constant? Still a big constant. So yeah, that you're right. That's a constant times a constant, still a big what? Constant. Later on, when you start changing the constants and you care that you're changing it, you'll put a little c and then you'll put a little bar over it to know that that C and that C are not the same C. They're not going to give you the same values. And what happens there is people will work with it, and they'll be changing the C out here, and after they find the C value, they don't know which one it goes back in for. All right. When we get to that, we'll deal with it. And I'll tell you how. Wherever you find C, that's where it has to go in. You can't go way back up there and put it in, or way down there and put it in. You got to put it in on the step you found it at.
Mr. Evans, when you take the derivative of u and put it, multiply it by the
Right.
dx, so whatever u is, do you automatically put it on the outside always?
Well, if you put a number here,
Uh-huh.
and you put 1 over the number outside, you're really just multiplying by 1.
Right, but do you always put the reciprocal of the derivative on the outside?
Well, you always put the reciprocal of whatever number you put here on the outside.
Right, but
If I want to put a 5 here, I got to put a what?
1 over 5.
If I want to put a 7 here, I got to put what? 1 over 7. Because there's other reasons to put numbers out there besides just the du.
But you
Alright.
always have to put the reciprocal outside.
Reciprocal out front, so that you're only multiplying by what?
1.
1. And see this one, what am I really multiplying by right here?
1.
1. But why could I not put that out here? Because it had what in
A
it?
variable.
Had variables. The only thing you can put, you can only put constants here and the reciprocals out front. You can't do that with variables. You cannot do that with variables. All right? Now, if you had this, you've got the integral sine x squared plus 1 x dx. See that x out front? I almost didn't put it there, but I need it. And if you wouldn't have, if this is exactly how you want it to start. Now, back row, that x was already there. I didn't put it in along the way, right? Now, this is your u. This is going to be your du. What is missing in your du? Okay, it's already got the x there waiting on you, but it needs a what? A 2. Now, if that x was not in this original problem right here, the x wasn't there originally, you'd have a really, really bad day. When you first start learning integrals, the variables are always going to match up for you. When the variables don't match up, you jump to a whole new world. All right? Like yesterday, when the variables didn't match up, you jump to a whole new world. Now, that's going to be 1/2. And if you have sine u, du, you know the rule says it's negative cosine. Okay, there was an x out front. Since I'm multiplying, I move the x over here. Because if I look at that and I see that that's my u, what do I know my u is going to have in it to be a du? It's going to have a what? An x. Notice if you can't do derivatives a little bit in your head, you'd be in bad shape. Now, honestly, what we should do is we should write this out to the end to help you. That's what we're not, okay. I try to write this down every time I work a problem. And I want to write it down every time I work a problem. And that's what's going to get you in trouble next year is nobody is going to take the time to write that down if it's this obvious.
Why is it -1/2?
Because the rule says when you integrate sine u, du, you get negative cosine u.
Oh, that's right, okay.
So, is this a rule or is this a reverse chain rule? Like
Okay, it is a rule that we use, but it's a reverse chain rule, and that's the reason the du is always going away. People always ask, well, what happened to the du? Well, what put the du out there? Taking the derivative. Okay, you're not listening to something I'm trying to explain. It's going to be a helpful bit. Because in a few minutes, somebody's going to say, what happened to du? I'm telling you now. When you took the derivative, it put the du out there. So what's going to happen when you do the opposite? The du's got to go away. Now, somebody says, but if the du is going away, why do we care to put that 2 there?
You gotta bring the 1/2.
Because if you don't put the 2 there, you won't put the what? 1/2 there. And if you don't put the 1/2 there, you won't have the 1/2 here. What happens, and it happens all the time, you watch students, you're grading their exams in a class, and they have this, but they don't have the right coefficient. Because they didn't put the 2 here, so they didn't put the what? 1/2 there. Now, somebody says, what happens if that x isn't there? Whole new world. All right? Don't even want to think about what happens if that x isn't there.
Is that where we get into like all changing into
You
trig?
get into all those methods that you get into, the methods.
Okay, what happened to the x at the front of the sign? You moved it back
Oh,
there?
it's multiplication because I need it in my du.
But, so the 2x isn't the derivative of the u?
Yeah. U is x squared plus 1. What's the derivative of x squared?
2x.
2x. Well, the x was already there. I just had to do what? Move it. Okay, if you're multiplying, you agree you can multiply in any order.
Mm-hmm.
So I picked that x up and I moved it out here to the end.
Uh-huh.
Because I wanted that x to be in my what? du. Because if I have x sign something, I don't have a rule for that.
Right.
But that x is part of my du.
I thought when you take the derivative of the u, you would do another
Well, what's the
2x.
derivative of x squared plus 1?
2x.
Right there it is.
She's saying
But,
she's saying you're missing an x. But
Yeah,
that x
wouldn't-
is the actual chain. It's like the second part of the chain. Whenever.
Okay, take the derivative of cosine x squared plus 1.
mm-hmm.
You get negative sine x squared plus 1 times 2x,
Yes.
right? There's 2x right there.
Okay.
Okay. Yeah. I'm not sure I'm answering your question, but I think you're trying to overcomplicate it. That's u, that's du. And the x was already in the problem, so I just moved it out here. And we don't need to take the derivative of 2x. We just take the derivative of the u right here. Is that okay?
Kind of, yeah.
The u is going to be the part right after the trig function.
I understand
We
that.
hope.
Yes. Can I show you?
Yeah.
Okay. This is what, right. If you're moving this x out here,
Right.
that would be,
It just goes, that's it.
but when you take the derivative of this, wouldn't you add another 2x?
No. Oh, no, okay. You already got the x there that you need. Okay. Okay, here's your u. And you want the du out.
Yeah.
Okay, you already got the x. You already got the dx. That's there. You just need to put in 2. Now, if you wanted to put in 2x right here, you'd have a problem. Because you can put 1 over 2 out front, but you can't put 1 over x out front. If you did it, and here's what's crazy, if you put 2x here, and then put 1 over x here, and 1 over 2 here, what's going to happen right there? Those are going to divide out. So the variables already match up. You don't need to worry about it. Now, if the variables don't match up, say there was an x out there. There wasn't an x out there to begin with, you can't work the problem without like a demonstration. Okay? Like that x, when I wrote the problem down, I didn't put the x there, but in my brain, I was already figuring out what the du was going to be. And I realized it was going to have an x. Because if I just had that and I had to put the x out there, can't do that. It'd be a bad day. Okay? Bad day.
Is this still recording?
Yeah. Now that you can work those, you can't work all those.
Okay,
How about taking the derivative? Rolls with the same derivative. Like, if you wanted to take the derivative with respect to x of an integral of 1 to x cubed
talked about yesterday?
T squared plus T
I'll show you
dt,
it in.
right?
Oh, I was trying to
Well,
find
what you can
pictures.
do, it's real simple.
I'm not
You
gonna
put
be,
the x
I don't
cubed
think I'm
in
gonna
everywhere
do
there's
that
one of
today,
these.
but I'll look at it tomorrow.
You get x is 6 plus x cubed. And then here's the part everybody forgets. See that right there? You gotta put in the derivative there. Then minus, and even if you put the 1 in here, what's the derivative of 1? 0. Now, if that were just an x, you'd have to put it in, plus x, and then the derivative of the x is what? 1. What everyone forgets when they use this little trick, this is Leibniz's, I don't know, but it's Leibniz's rule, is everybody forgets to put the derivative right there. All right, now, what you can do, since this would be easy to integrate, is you can integrate all this, substitute this in, then take the derivative, and you're going to get the same exact thing. But that's Leibniz's rule, and what it says you have g of x to f of x, d over dx of some function of t, dt. Then what that will always equal is h of f of x times f prime of x minus h g of x times g prime of x. And what everybody forgets, the reason they forget is when they teach this, they start off just using an x. And so they go, oh, well, you just put an x in everywhere there's a t. Yeah, but the derivative of x is what? 1. So you've got to remember to put that on here. That's Leibniz's rule. Take the derivative of the number. And it's a lifesaver because you don't, if you had some over here that you couldn't even integrate, it doesn't matter if you got Leibniz's rule. Yeah. Just remember, give Leibniz credit for it, okay? Give Leibniz credit. Yes, ma'am.
I started on it and I'm getting a bunch of I can get her. So you want to say enable and then I'll.
Now, get it paid for without her knowing.
I'm gonna send it out to her. And then I'm gonna email our representative and just say, I don't need this stuff, like it's done, you don't have to send that to us, just so she doesn't.
But if you do end up with one you need, just go call.
Thank you,
Okay,
sir.
that's me. All right, here we go. Hey, it's a good day. I got to teach something I like teaching. Everybody sprayed their desk, right? Sprayed your desk, got a water bottle on the floor, but I bet it belongs to somebody. I got children that can't pick up their water bottle.